Okay, so first one, this is being given for in physiology or medicine. Now they have been given for telling the or for the topic related to peripheral immune tolerance. Now there is a lot of thing that you need to understand before understanding this. Now let's start. Okay, so सबसे पहले this is a bone, correct? You might have seen this Tom and Jerry and all. So this is a bone. Now inside it is something called bone marrow, correct? Bone marrow is inside it. Some people eat it also. Okay, so that is bone marrow. Now bone marrow is very important. Why important? Because all your, yes, they produce a lot of different kind of stem cells. Now they make pluripotent stem cells. Now stem cells, for you, stem cells are the cells which generates other cells. Okay, not every cell can be divided into different cells and form new cells. There are some specific stem cells, they are present for every different kind, like RBC, WBC, skin cells. So all these cells have one specific stem cell, so that stem cell generates all of them. Okay, so now those stem cell which is generating your entire skin, let's say, or which is generating your entire blood cells, now that is made in the bone marrow. So this is pluripotent stem cells. Now this gets divided into two. From this bone marrow itself, you get something called B cells. So this pluripotent stem cells, it forms other cells. So one of the cells it will form is B cells. This is white blood cells, you understand, WBCs, that are used to protect you from diseases and all. So this is one type of white blood cell. Now the other goes into thymus. The other kind of cells divided gets into thymus, and it matures in thymus eventually to make something called T cells. These together are called usually WBCs. That is T cells and B cells. Understood? Bone marrow has some different kind of cell that generates two other cells. B cells is directly generated. T cell is generated via thymus. It matures in thymus. That is why, because of this T only, it is called T cell. Okay. Now both of these then are released into your blood. Both of these are released into your blood. Now what they'll do, if you have any infection, if you have any different kind of diseases, it will fight it in your through your bloodstream. Understood? Now okay, then T cells are mainly of two types. What is this? CD8 plus, these are killer T cells. So what they do, these T cells have a function that, now see, if your body is caught with some pathogen, some disease, now some of those cells are affected. So what this T cell does is it destroys the affected cell. First you have to, of course, to reduce or to stop the further expansion of that pathogen to your entire body. What you have to do, already those which are infected, that has to be killed. Okay, so that killing is done by this kind of T cell. Okay, the other one is this helper T cells, which generates different kind of cells which help B cells to function. So this one helps B cell to function, which is to generate antibodies, this, that. So this generates antibodies, and this one are the killer cells. So they do what? They kill the infected cell. Now there are many types of this. what we have to study here, or what they got the Nobel Prize here for, was for a specific T cell called Treg T cells or regulatory T cells. Now, your body, if anything, any pathogen enters in your body or anything gets infected or defected, these are the two things, or WBC fights it. Now, how does WBC fight it? It produces B cells. B cells produces antibodies. Antibodies fight that particular pathogen. T cells does what? T cell does two functions. One is helping the B cells, which is helper T cells, and other is killing those cells which are already infected. So these are the two functions of T cells. Understood? Now, in this helper cells, there is one regulatory T cells. Now, what does regulatory T cell have? See, usually what T cell is doing? T cell is like an attack weapon, like a tank. It is going, and whatever cell it finds that it is already infected, it destroys it completely. Now, this regulatory T cells are like brakes to that tank. It acts as a brake, as in, if it is going and destroying all the cells, then if there is a cell that is of your body itself that is not infected, then that also can get killed, that also can be killed by the same T cells. So this regulatory T cells identifies the normal cells and reduces the impact of this killer T cell. That is, it saves the normal cell that is not infected in your body. This is the work of regulatory T cells. Okay, you will understand all this better when you have done the science and tech classes. Okay, that I have not started. Who has done? You have done it. Okay, that's it. Okay, so these are the different kind of cells. Now, for now, regulatory T cells are those cells, those T cells which stops other T cells to destroy the good cells. That's it. Now these regulatory T cells are usually produced by a particular gene. So a particular gene called FOXP3. So FOXP3 gene is responsible for creation of these regulatory T cells. Okay, for regulation and how it will function, everything is controlled by FOXP3 gene. Now a simple understanding will tell you, now if I have, now this is doing what? This is stopping my T cells to destroy the good cells. Now if there is, now if this FOXP3 cell has some, gene has some defect, if it has some defect, what will happen? This Treg T cells will stop working properly. Then what will happen? If this is not stopping the good cells to be destroyed, then what will happen? Your body will start destroying your own good cells. That is what is called autoimmune diseases. For example, in type 1 diabetes, what happens? It destroys your cells that produce insulin. Okay. Similarly, in different kinds of cancer also, you have similar things. So what is happening here? Now, if this connection is destroyed, what will happen? Your body will not stop or save your non-infected cells. And if it won't save your non-infected cells, you can have autoimmune diseases. What is autoimmune diseases? When your immune system starts attacking your body itself. Understood? Little, kuch, huh? Okay, this much only I can explain for now. Okay, once you do the science and tech lectures, everything will be much more clear. I hope it is clear to you at least. Okay, so this is what they have done. So now what they have done, their discovery is finding this connection. And now just understand, if I make changes in this FOXP3 gene, because I can make genetic changes, then I can reduce or increase the impact of this cells. Correct? Regulatory T cells, I can increase their impact or decrease their impact. Based on that, I can have different kinds of therapies. Understood? For example, let's say if I have to my finger got cut. Now I am putting another prosthetic made finger on here. Now what immunity usually does? It rejects it because it comes from outside. So there is huge probability of rejection. Why it rejects it? Because it is not from the body itself. Now if I reduce the impact of this, that is regulatory, if I increase the impact of regulatory cells, what they'll do? The T cells which destroys the new prosthetic cells, impact will reduce and it will settle in my body fine. Okay, so one way is I can, using this gene, I can either increase its impact or decrease its impact, and both have their applications. So this is what they have found out. First person was the first scientist found out this, that there are some regulatory T cells. The other two found out this FOXP3 gene, did some experiments on some mice to understand this linkage. This is what they have got Nobel Prize for. Understood? Okay, then yeah, now what it says, winners. So winners are this guy Sakaguchi and Mary Bronco and Fred Ramsdell. Now he is from Japan and these both are from USA. Does not matter, nobody is going to ask you. Now, citation for discoveries concerning peripheral immune resistance, immune tolerance. Now, there is one immune tolerance that is found in the thymus itself that stops your T cells from attacking the normal cells. Now, this one is called peripheral immune tolerance because these are generated outside the thymus cell. That much only you have to understand. What is that immune tolerance? Immune tolerance means usually what happens, T cells attacks anything that comes from outside or it is not proper. This reduces that. So peripheral immune tolerance. So it is increasing the tolerance towards slightly infected or some pathogenic some cells. That is same thing, trying to protect your normal cells. Then what is immune tolerance? See, central tolerance, self-reactive T cells deleted in thymus. Then peripheral tolerance is regulatory T cells. This is the tricks that we understood. This suppresses runaway immunity in tissues or lymph nodes. That is outside your body. It suppresses the other T cells that can destroy the normal cells. Now the first one, what did he show? He showed this immune police or regulatory T cells exist. Then the other two, in scruffy mice, a kind of mice, they pinpointed FOXP3 mutation causing fatal autoimmunity. So basically, using this disease, what they established? They established relation between FOXP3 and regulatory T cells. This is what they did. So these two did this. He first discovered about immune police or regulatory T cells. Then, now you can have many IPEX syndrome or different diseases in human because of this. Now, FOXP3 is the master regulator of Treg development and function. This you have understood. That's it. Now, see this directly. Now, if I deplete this regulatory T cells, if I deplete them, what will happen? Augment cancer immunotherapy. Now, what happens when I have, see, cancer cells are not good cells, correct? So usually your T cells does what? It destroys those cancer cells, correct? So this is, let's say, this is cancer cell. So what your immune system does? Your immune system attacks it, correct, as it should. Now this regulatory T cells इनका तो बस काम ही है, they are like brake. So it is stopping this T cell also, which is doing a good work, that is destroying the cancer cells. So here Tregs are doing what? It is stopping this stopping the T cells from destroying the cancer cells. So this is bad. So what I can do is I can remove these Tregs or I can reduce their quantity. Then what will happen? खुली छूट मिल जाएगी मेरे T cells को cancer cells को attack करने के लिए. So then my T cells will attack the cancer cells fully and probably destroy it. Understood? So this is what we are doing here. See, deplete Tregs will augment cancer immunotherapy. Correct? This will be done. Then next is expand Tregs. Now if I increase the concentration of these T regulators, now what will happen? Treat autoimmunity and tolerance in organ grafts. Now what your body was doing? Your body was immediately attacking anything that was coming from foreign particle, like the prosthetic finger that I added. Now I can increase the quantity of Tregs. What will happen? This attacking, it will be stopped and this prosthetic will be properly laid on my body. So this is the second use. One is with respect to depleting it, one with respect to increasing it. How you can change it? Using the change in gene. This is what they have discovered. Now the second one. This is easier. Okay, this is for chemistry. Then this is fairly easy. See, okay, so it's a structure like this. Now it is given for all these points that you see are actually metals. All these joints that you see are metals, and what they are linked by, that is the white portion of it. The white portion of it is organic. This is organic molecules, and the yellow portion of it, yellow portion, yellow dots, this is metals. So basically they have made organic metal honey web like structures. So this is in 3D. In 3 dimension they have made this structure, okay, which has metals all around it and connected by organic molecules. Now what good it does, now you can see that there are small pores here, okay, much smaller pores. Now these pores, when it is in 3D, what it will do, it can absorb different kinds of gases, different kinds of nutrients. You understand this? So it can absorb different, in the spaces that it has, it can absorb different gases, nutrients, this, that. So then how it can be used? For example, one very simple use is it can be used for carbon sequestration. So CO2 is there. Now you use this material, what it will do? All the CO2 will get absorbed or stacked here. Then what you can do? You can simply remove this. Understood? So these are microscopic in nature. If you have to understand it like you might have seen this. You have seen chairs like this. Chair where you are sitting, okay, it is also those webbed chairs you have seen, which have white. Correct? Those webbed chairs you might have seen. Okay, so understand it like those webbed chairs are made up of the molecules of organic molecules, and the end points are the metals. Now you take that chair and you make a stack of it. That becomes a 3D structure. That is what they have made. Now it can be used to absorb many different kinds of things, and it can be used in many different applications. That's it. Yeah, so they have been given this for something called metal organic frameworks. Now, winners are this Kitawa from Japan and this is from Australia, this is from US. Names are less likely to be asked. Then, why they have been given? For their groundbreaking creation and design of MOFs. MOFs are what? Metal organic frameworks. You understand the framework? Then, now, what are MOFs? They are crystalline materials made up of metal nodes linked by organic molecules. Now, of course, they have spaces in between them, so they are porous, sponge-like networks with tunable holes. Now, what they have found is, now the holes or what is the size of the hole that I can vary, correct? Because I have formed that metal and organic polymer chain, now I can change the orientation. For example, if it is like this, now I can tighten it in a simple way. I can tighten it and the holes will become smaller, correct? Or I can loosen it and the holes will become bigger. Now, based on that, at a molecular level, they can do this. Then what will happen? They can trap different kinds of gases based on their atomic size. So CO2 has different atomic size. Now, if I have to capture H2, that is hydrogen, so I need smaller pores. So I'll make the pores smaller. Or if I want to trap something else, then I can make the pores longer or bigger. So this they can keep on changing. This is metal organic frameworks. Now, this is what is written with tunable. जैसे tune करते हैं radio को. Similarly, you can tune the holes also. Size big, size small, whatever. And it is a 3D structure. I have drawn 2D because I can draw 2D only. Okay. So that's why I have drawn 2D. It's a 3D structure. Okay. Then. Yeah. Now, see these three scientists, what they have done. See, first is this Robson. Robson has done what? Early 3D metal organic networks he made. Now, showed large internal voids or porous materials. So, first time he made 3D metal organic networks. This is the guy that made that network. Now, next one. Kitagawa. What he did? He proved pores can absorb, expand or contract with different kinds of gases. So that guy just made the framework. This guy showed that it can absorb different kinds of gases, based on it expand, contract, this, that. Then this was important because then gas capture and storage was possible. Okay, then next was Yaghi coined MOFs. So this term was coined by him. Now he founded reticular chemistry or rational design of targeted structures. So this one find out that because of different kinds of gases, it is expanding and contracting. This one find out that we can make different substances, or he found the method to make different kinds of substances with different tunable holes. So first discovered that we can make some structure like this, some framework like this. Second one, observed that some gases can expand it or contract it. So we can think of tuning this based on the gases. Third one, find out the reticular chemistry or the mechanism to do this. That is tuning it. That's it. Now, why are they special? They provide ultra high surface area with tunable pore sizes or chemistry. Okay. Then selective trapping or separation of gases and molecules. You understand selective trapping? For example, I had like this, and this was naturally trapping CO2. CO2 is a big molecule, so CO2 was getting trapped here. Now, I take this same metal organic and I alter it a little. To produce what? To produce smaller holes. Now, smaller holes can capture what? They can capture hydrogen. So, based on the pore size, I can change it, which gas it will capture. Then, so this is selective trapping. Then, yeah, modular design is fine. Then see key applications. This you'll understand. One is water harvesting from desert air. Now desert does not have water, but the air still has water vapor in it. we are not able to capture it. Now if I can design something like this exactly at the size of water vapor, then what will happen? Vapor get entrapped here, and then I can use it. Of course, a future technology that can be in application. Then next is carbon capture and storage. This is the main use it is being touted for. That is carbon capture and storage. Then next is storage or separation of toxic or industrial gases. Correct? Based on the size of gases that is released, you can tune it. Then next, custom chemical processes. For example, catalysis, selective reactions. Now this can be used as a catalyst also. Why? Because it provides a very large surface area for different kinds of reactions. So it is in layers. Okay. Now if I tell you 1 gram of it, it may be small, but it provides enough surface area equivalent to a football field. How it will provide enough surface area? 1 gram of it is very small, but it is very small, so layers. Now each layer provides some surface area, correct? Let's say this surface area. Now if there are lakhs and lakhs of layers like this, so if you add 1 lakh of this, you get the football field like area in just 1 gram. Now of course for you it is just a small thing, but for molecules it's equivalent to having a football field of area or just this small material providing enough surface area as that. So there it can be used as a catalyst or for propagating different reactions. Then energy uses, as I explained you, H2, CH4 storage, batteries and all that can be used. Understood this? This you got? Okay. Then okay, let's do the other topics first, then we'll come to the physics one. Okay. Yeah, let's do this. Niti Aayog. Chitra, you are getting it? Okay. Then, so Niti Aayog, this is simple. So what they have done, they have made, see, the concern is everything is getting absorbed in artificial intelligence. Now we have a huge population that can be left behind from this revolution. Okay, so what we need is inclusive AI. So for that they have come up with different kind of roadmap. Okay, so AI inclusive roadmap, Niti Aayog has come up with it. Now see, some people just don't see. What do you think, like poor people, how they can use AI? How can AI be useful to them? How can they use AI? Yes, language translation. So basically, see, the thing is, you are also not developing AI. ठीक है, आप भी कोई इतना कुछ मचा तो नहीं रहे हैं. You are also just using it. Now, if I make it more user friendly, then they can also use it. Correct. Right now, for example, if I make right now using Chat GPT, you can give me the information that, let's say you take a picture of a field and then you ask Chat GPT, please analyze what might be the moisture content of it. Now it can analyze it, it can tell you it looks like it has 14% moisture content. There are developed mechanisms for this. Now it can do this. Now you think you have done this, but you have not done anything. What you have done, you have posted a picture and posted a query. Now if he can do it in his own language, while just saying it, and the result that comes out of it is not in form of text but in some form of color coding or something, then he can also understand it and use it. For example, he has this AI board. Now he posts picture of his field. Now based on the moisture content, if the moisture content is enough, it shows as green tree. If it is slightly less, it shows as a yellow tree, and if it is very deficient, it will show as a red tree. Then it will do what? He can simply water them according to it. Similarly, he can do it for different nutrients also, for phosphorus also. So this can be done. Now of course Chat GPT does not have the property to understand phosphorus or different kinds of content, but it can be done. There are many AIs doing this. Okay, fairly simple, you can get from the surface. Now So similarly, you can have voice AI, okay, then AI in vernacular languages. So all these, then giving micro courses to these people, micro courses to how to use this AI, how to take photos, how to upload them, how to get information about your field. So all these comes under micro courses. So this is government, what this is what is government is trying to do, provide different kind of voice AI so that he can just ask, correct. Similarly for vernacular languages, so that different languages can work with the AI. Now this work won't be done by the big companies, big tech won't do this, correct. Why would big tech invest so much to develop everything in Kannada? It is not important to them, okay, but it is important to us, correct, because our farmers or our people who are not that well educated or educated in only one language need it. So we need to develop it. So for that they have made one mission. Understood? Now other things are factual in it. Yeah, use AI and frontier tech to raise productivity and protection in the informal economy. Now, what the aim in one line is, right now AI is totally white collar centric. Only white collar people are using it. So from white collar focus to Bharat's informal workforce, they want to take to them also. Then beneficiaries, as you can see, farmers, artisans, gig or contract workers, street vendors, healthcare aides, all these can use AI in different ways. Then this is going to impact, this is launched by Niti Aayog, will impact 490 million informal workers. Other details you anyway will remember now. Okay, Niti Aayog has launched this, it will impact 490 million informal workers. That's it. 500 भी लिखोगे कोई दिक्कत नहीं है. What gaps does it address? So financial insecurity, weak social protection, this. Then now this is one portal, one mission they have started, Mission Digital Shram Setu. Shram means what? Yeah, Shram means hard work. So basically it is related to people who are laborers. Okay, so Shram Setu is basically trying to, Setu means what? They're trying to bridge gap with them. Okay, so what it will do? It will link informal workers to digital tools using AI, blockchain, immersive learning. So basic micro courses and all this will be designed and delivered to them. Then outcomes, better skills, that you can understand. Then you come to new Antarctic research base. India has started the work on it. Okay, that is Maitri 2. Okay, so the money was government approved Maitri 2 2000 crores. Okay, so government has approved this much money for Maitri 2. Now completion by January 2029 will be India's 4th Antarctic base. Now most important thing in this topic is to remember all the bases. So first one was, wait, yeah, what are India's Antarctic station? First one was Dakshin Gangotri. This was the first one. Eventually it got decommissioned. Okay, not in use now. And then second was Maitri. This is working since 1989. Then next was Bharati. It is working since 2012. Now we are going to launch Maitri 2. From Maitri 1 to Maitri 2. This has been approved. It is upcoming. Till when it will come out? It will come out December 2029. Okay, one more thing that you have to remember is there is one Arctic station also called Himadri. Himadri is in Svalbard, Norway. Understood? Now they are all managed by this you have written, correct? Now yeah, they are all managed by NCPOR, that is National Center for Polar and Ocean Research. this name also you can remember. NCPOR manages all these stations, all the 4 stations, one decommissioned and one has to come. So 2 stations right now in Antarctica and one in Arctic, that is Himadri, is managed by NCPOR. NCPOR comes under, this is the nodal agency, and it comes under Ministry of Earth Sciences. That's it. This is what you have to remember in this topic. Names, where are they, and who is regulating it. Then, now, what do these polar stations do? Okay, why do we have polar stations in the first place? First is climate monitoring. Okay, it will give us sharper monsoon forecast. Now, if you know about polar vortex. Polar vortex, you know. Okay, so there are different phenomena in the polar region that affects the atmosphere or affects the weather of different parts of the earth. Okay, including that of India, equatorial, all regions are affected. Those wind cells, you know, so they form cells, correct? So everything is connected to everything. Whatever happens in the North Pole or in the South Pole also impacts you in some way, weather wise. Okay, so that climate monitoring is done. Then glacier or cryosphere science. Now, if we understand the glacier or cryosphere science, then it will help us also understand Himalayan water security, because it also consists of ice, cryosphere, all that. Then ocean and sea level trends, coastal protection, everything is connected, because if from the ice melting, it gets converted into seas and then it is transported around the world. You understand this? So polar regions have 6 months of summer, 6 months of winter. So during summers there is melting. In the melting phase, it melts and gives water to the ocean. Understood? Okay. Then atmospheric or space weather is fine. Global scientific presence. Now we are part of Antarctic Treaty also, and also we also have, if you know, these are also sectors of influence in international politics. So there also, that's why we have a center there. Then base and logistics for Indian expeditions support. Now if we have to go on some expeditions, we need a base. For example, expeditions as in marine expeditions, if I have to go, then I need a land base. So where are these bases? These bases are my Himadri and Bharti. So these are the bases from where I can send marine expeditions or different kinds of expeditions. Okay, that's it. Now we come to Physics Nobel Prize. Okay. They have got this for quantum tunneling. Okay. Now, what is quantum? Quantum mechanics, you understand? No. Yes. So basically, when you go to quantum level, that is the atomic or subatomic level, that is at the level of atoms or electrons, what will happen? It has been found that the classical mechanics that you understand, classical mechanics is what? That a car goes at 40 km per hour. Okay, so in 1 hour, how many kilometers it will reach? 40 km. Correct? So all this is classical mechanics. Whatever mechanics or physics you understand is classical physics. Now that stops working here. Okay, this does not work here. Here some other kind of mechanics works, that is called quantum mechanics. Okay, we don't know it fully, nobody understands it fully as of now. Now different concepts we keep on understanding, and that becomes news, that becomes important for us. Okay, nobody understands quantum mechanics fully. Now, the concept that we'll be dealing with today is quantum tunneling. Okay, now this is a guy. Now this is a ball. He throws the ball. Okay, now he's a small kid. He cannot throw it beyond. Not possible for him. Okay. Now, if he throws the ball to the wall, what the ball will do? It will come back like this. Correct? It will bounce back towards him. Now, this is what happens in normal mechanics. Now, in quantum mechanics, when you are dealing with very microscopic particles, what we have observed is a phenomena where if a particle, or in this case, let's say a ball is thrown like this, then it does not have the energy to cross the wall like this, go above it, but it forms some kind of tunnel, and it is seen to be here. Now, how does this happen? Understand, usually what you see, everything has two senses. There is, you know about particle and wave duality. So there is duality between particle and wave functions. Now, everything has a wave function also, is a particle also. Now, just understand it in very basic way, that if there are electrons here and there is something that is stopping the electrons, what we have seen is some electrons, not all of them, but some electrons will reach here irrespective. Now, in the quantum world, there is nothing is permanent. Basically, you cannot say that electrons are here and no electrons are here, because the wave function just moves forward or does not believe in any stoppages. So wave function cannot be stopped. That's why most probable, if I ask you the term that we usually, in general sense, like in our general mechanics, I am on stage. Am I on the floor of the class? No. Understand? I am on the stage, I am not on the floor of the class. This is classical mechanics. In quantum mechanics, I will say I have a very high probability of being on stage. I have a minuscule or very low probability of being on the class floor. But there is always a possibility. That's the only difference. Most probable is still electrons being here. Now, this is called non-zero probability. So electrons, even with this barrier, has non-zero probability of being on the other side. Now, why is this non-zero? This is because of a phenomena called quantum tunneling. That is the tunnel that I made there also. This is because of a phenomena called quantum tunneling. Okay. Now, understood this much? Just take it as it is. Nobody understands why exactly this happens. Okay. So people who is telling you, or the person who is telling you, also have just understood it. It works like this. Why is very difficult for anybody right now, anybody in the world. Just understand how. Okay, here in normal mechanics it cannot work like this. Anything is at a permanent place, at other place it is not there. In quantum mechanics it is said it is more probable to be at some place. It has a non-zero probability of being somewhere else also, even if there is a barrier. Why? Because the barrier can be crossed by something called quantum tunneling. That's it. Okay. Now, what they did this. Now this is a battery. Now they connected this whole thing in a circuit. On one side you have a superconductor, on the other side also you have a superconductor. This is divided by a thin insulator. Okay, this is being stopped by a thin insulator. Insulator is what? Which does not allow electricity or electrons to pass through it. Correct? Superconductor is what? Superconductor is what? Conductor is what? Conductor is which conduct electrons or allows easy passage of electron. Superconductor क्या होगा? It will provide almost no resistance to electrons. So they will pass very smoothly. Correct? So this is superconductor. Now this superconductor is a very good conductor of electrons or electricity. This part also, but it is being stopped by a thin insulator in between. Now ideally no current should flow. Correct? If you take some, because of this insulator, now the electrons cannot pass from here. Correct? This is will not allow electrons to pass through it. Correct? And the electrons cannot flow back. So then there should be no electricity or no passage of current. But it was observed by them that this is being followed, that there is still flow of current. Now this flow of current at extremely low temperature and extremely high superconducting material. So the conditions are very tough to create, but eventually they created something like this at very low temperatures, because superconductors exist at very low temperatures and some very difficult conditions. They made something like this where the electrons are somehow crossing from here to here and there is some current in the circuit. Okay, now this is, how can this happen? If this is a perfect insulator, it should not have been possible, but it is possible because there is quantum tunneling. Now quantum tunneling, before this experiment, before these people, was shown in very microscopic particles somewhere far, very small in some conditions in the lab. Okay, now this was big enough to be held in a hand. Okay, so now the main thing with quantum technologies is it is only done at a very microscopic scale. Now if it can be done at a macro scale, then you understand, then every barrier will not stop you if we can somehow utilize this technology, okay, to pass the barriers. Now this is the first demonstration of it, that is something which can be seen by you, can be held in your hand, is showing quantum tunneling. This was done like a few decades ago by them. Now they are getting the Nobel for it. Okay, now this is not some far off technology. The phone that you have right now, you have memory cards, you have SSD cards, those are also using quantum tunneling. Okay, what is happening inside your SSD cards? There are oxide layers. Just like you had superconductor there, you had two oxide layers, and in between you have an insulator. Still there is passage of electrons or information between these layers. Why? Because of quantum tunneling. Because of this only, because of this phenomena only, otherwise you will always have to provide energy to create anything. Now because of this phenomena, information can pass this fast between your phone and it can be processed so fast because it is going through quantum tunneling. So that is why it does not have to go through any barrier like this. It goes straight through the barrier. Okay, now this is the phenomena that is being used in different devices also. This is quantum tunneling. Now they were the first proponents of it, and the first one gave the theoretical one and the others showed this in a supercooled insulator and superconductor arrangement. This arrangement is called Josephson circuit or arrangement. We'll see about it. So this was shown by them. This is the demonstration of quantum tunneling at macro scale. This is what gave them Nobel Prize. Now see, So winner is John Clark, Michael Devon and CDMA. Okay, like civil disobedience movement, they are CDM. Now, citation is discovery of macroscopic quantum tunneling in superconducting circuit. Every word you understand? Macroscopic at a macro level, quantum tunneling in a superconducting circuit. That was a superconducting circuit. Now, what did they show? They show large visible superconducting circuits can display quantum behavior. So they were large enough, they can be held in hand, they were of this size. Okay, so they have shown this. Now at ultra low temperatures, circuit states switch by tunneling across barriers, or abrupt transitions were observed by them. Abrupt transitions means now electrons are here, they should pass over a barrier and some electrons may go there because of the energy provided, but they saw that electrons are moving without any barrier. Why? Because they were following quantum tunneling. Basically it forms a tunnel like structure and the electrons can go beyond. Then what is quantum tunneling? Now see, a particle has a non-zero probability of being found beyond a barrier it classically cannot cross. So in classical mechanics it cannot cross the barrier, but in quantum mechanics it has a non-zero probability of being on the other side of the barrier. Okay, this is quantum tunneling. Now why this happens? This happens because of due to wave particle duality. The particle's wave function spreads into or through the barrier. So particle cannot go, but the wave function is not stopped by any barrier. So it goes through that barrier, and because of that there is some probability of it being on the side also. Though not most probable or always there, but some probability is always there. Then giving a chance to appear on the other side. Now this is Josephson junction. The thing that we draw, two superconductors, a thin insulator in between, that is called Josephson junction. Okay, two superconductors with a thin insulator or copper pair tunnels, precise current voltage one. This is just this much. Two superconductors with a thin insulator. This is the junction that was used. Now why does it matter? Now see, in quantum computing this can be basis for superconducting qubits and quantum sensors. Okay, for example, the qubits you understand, like you have bits, similarly you have qubits. Qubits is used in quantum technologies. They can have different kinds of quantum properties. One of them is tunneling also, so that can be shown. It's fine. Then beyond classical limits. Now this is also fine. Then where is tunneling used? Now see this. This is atom scale imaging, STM. Now what they do, they have different kinds of, they have STMs or atom scale imaging. So what it does, it reaches this, let's say this is a needle like structure, it has a some very small particles just, and it will keep this just above the surface it wants to capture or understand the structure of. Now what will happen, because of quantum tunneling, suddenly this particle will get onto the surface, and then with the movement of this needle it will go around the surface and it can come back and give the information. This is quantum tunneling. This is quantum tunneling or use of quantum tunneling in this. Okay. Okay, वो टनल बना ही रहा है. Then flash memory or SSD cards, this you have already understood. Then Josephson device and squids. Okay, then quantum computing qubits, this is fine. Now nuclear fusion, this you understand. All these names are fine. Now nuclear fusion, see, if you might have heard, for doing a nuclear fusion reaction, usually the nuclear fusion reactors also uses nuclear fission. Why? Because that amount of energy to combine the hydrogen atoms can be produced only by nuclear fission, correct? Otherwise two hydrogen atoms, see, hydrogen atoms are what? they are essentially protons, no? They are protons, correct? Now, why will they come close? They should repel each other. They will repel each other. Same charge always repel each other. So, they have a barrier, that is the barrier of repulsive force, that is not letting them come together. Now, using nuclear fission on Earth, what we do? Using nuclear fission, we make it overcome this barrier and then get combined and release energy. But something like this is not happening in the sun or other stars. Correct? So there is no nuclear fission to power the nuclear fusion. The entire sun is powered by nuclear fusion itself. Now how this is happening? This is also explained by something called quantum tunneling. So this is also a repulsive force, like a barrier that is stopping it. Now it can go through this barrier through a tunnel that it can form, and this can also be explained by quantum tunneling, that is nuclear fusion in stars or reactors. Understood? This can also be explained by quantum tunneling. Okay. Okay. Now, let's just revise first, वरना तो आपका गायब हो जाएगा सब. Yeah, let's revise first. Now, first topic was, now you have to say, first topic was peripheral immune response. Now, what were the main actors in it? There was something called T-rex, correct? So there were regulatory T cells, and they were controlled by something called FOXP3 gene, correct? Now, ये regulatory T cells क्या करते थे? What they used to do? They were like brakes. ये brakes किस पे लगाते थे? Other destructive or killer T cells. Why brake क्यों लगाते थे? To save the non-infected or good cells. Correct? This was the entire thing. Now, if this gene starts, if you have defect here, then this also gets defected. Then what will happen? These other killer T cells will start affecting your good cells also. Now, there were two things. If I somehow, by changing this gene or whatever, if I increase the concentration of regulatory T cells, what will happen? It will decrease my what? If I increase regulatory T cells, what will happen? Yes, it will reduce my immune response. It will reduce my immune response, correct? If I increase this, it will reduce my immune response, because it is like a brake. So it will stop my or reduce my immune response. Then where this can be used? This can be used in organ transplant. The other way is, if I decrease it, then what will happen? Yes. So then what will happen? If I leave the brake, then what will happen? My vehicle can go very fast, and this is a attack vehicle. This is like a tank. So what it will do? It will destroy all the infected cells. That is, this will increase my immune response, and this can be used in cancer therapy. Correct? Because in cancer therapy, you have to destroy your own cells, okay, the infected ones. So this can be done. This is the only thing you have to remember in this. इतना तो समझ आ गया? आगे? हाँ? Okay. So this is about peripheral immune response. This is why they were given Nobel Prize in medicine. Then next was MOFs, metal organic frameworks. This was easier to understand. So basically, you make frameworks like this. On nodes you have metals, and these chains are made up of polymers or organic polymers. Now what you can have, you have pores in between. You can increase the pore, decrease the pore. Based on that, gases, what gases are getting absorbed can change. Based on that, you can have different mechanisms or different uses. Correct? It can be used in carbon sequestration, it can be used in hydrogen storage, it can be used in many other things. Understood? Now next was what? Niti Aayog. Yeah, that is fine. Niti Aayog, they have developed some AI roadmap, okay, to include different kinds of people, or beneficiaries are usually people from informal sectors. So it tries to include people from informal sectors in AI applications. You understand how they are trying to do this. Then other one was, yes, Antarctica Research Center. What you have to remember, Antarctica के कौन से हैं? There was first one that, yes, first one was Dakshin Gangotri. This is not in use now. The second one was Maitri, commissioned in 1980, 82, 89. Okay. Then next was Bharti. Bharti was commissioned in 2012. Then now we are planning for Maitri 2. This will be 2029. Correct? Now for Arctic also, you remember Himadri. This was, year was 2008. Okay, these names are important. Other than that, generally you can understand that all your weather patterns, all your sea patterns are getting affected by the whatever happens on the poles. Correct? So there are two things. One is it will be used in weather forecasting, this that. It will be also used in sea level understanding and sea related phenomena. And the third thing is it will be used as a base for your expeditions. Okay, and one point from international relations, that we also want to have our influence in the Arctic and Antarctic region, because these are global commons. If you know, Antarctic is global commons, so we also want our interference or our influence there. Understood? Fine till now. Now last is this for physics. This is given for quantum tunneling, that was shown in macroscopic superconductors. Okay, here what you can remember is this diagram. This was the superconductor, this was also superconductor, this was insulator, and there was some tunnel that was forming in between. Correct? And other diagram, that if a question comes in main, you can draw. This is your barrier. Now here just draw electrons, many electrons, and write here most probable, and here just write one and say non-zero probability. Why non-zero probability? Because there is always probability of quantum tunneling. Quantum tunneling is what? Quantum tunneling is movement of these subatomic particles beyond a barrier that cannot be crossed in classical physics. That is quantum tunneling. Now because of this you can explain many different phenomena. One of them was nuclear fusion that is happening in different stars and all. You can also explain what you are using it, for example SSDs. Okay, then I explained you one of the imaging techniques where it is used. So all these are uses of quantum tunneling, will also be used in quantum computers and emerging quantum technologies. Okay, this is about quantum tunneling. Now one more name was there, that was Josephson's what? Junction. Yes. This is what they had made. Now they had made it at very low temperatures. Correct? There only superconducting can exist. This much you understand? Okay. This much only is needed. Okay. Then let's come to questions. Okay, do this. What do you think? Huh? C? Raise your hand for C. Okay. What it says? See, first statement is depleting tracks can enhance anti-tumor immunity. This is correct? This is correct? If you are depleting tracks, then anti-tumor immunity or immunity against the tumor will do what? Now, this you are decreasing. So what will happen? Your immune response will increase. So it will enhance anti-tumor immunity. Yes, correct. Then next is because tracks always promote tumors by directly mutating oncogenes. No, it does not do any direct promotion or directly mutating this there. What it does, it is just like a brake. It does not kill the entire cells on itself. It does not do anything on itself. It's just like a brake. Okay, so just brakes means what? Now if like my mom, when she drives a scooty, she usually just presses the brake all the time कि कभी भी रुकना पड़ सकता है. Okay, so slightly her brake is pressed all the time. Now sometimes when she is feeling free in life, then she leaves the brake. Okay, and other times she just applies it completely. Now that brake is like T-Rex. So T-Rex are just the brakes. It is not driving your entire vehicle or doing something different. Understood? So directly mutating and oncogenes are genes that are causing cancer. That is why they are called oncologist. Okay, so this is not doing something like this. Answer becomes A is true, R is false. Okay, then what do you think? Correct? Two are correct. Which ones are correct? First one and third. This Robson guy gave the early 3D metal organic framework. Then MOFs are generally non-porous due to dense packing. No, their main property is being porous so that it can absorb gases. Okay, then MOFs enable selective gas separations. Yes, we have understood this based on size. Now one thing, please don't do wrong, is this absorbs gases. It does not absorb gases. There is a difference. Absorb means what? Just on the surface it will take all the gases. Absorb means what? It makes it completely or engulfs it. For example, you absorb, when you eat food, you absorb the nutrients. That is, you completely take it in. Absorb is simply all the when you go out and all the particles from the coal and other things that gets on your face, that is like absorption. That is just kept on your face, on the surface. So it is doing, because it is a surface related phenomena entirely, so they are absorbing. Okay, UPSC has already interchanged them to make a wrong statement. So there is adsorption, not absorption. Okay, then MOF enables selective gas separation. This is correct. So two of them are correct. Then last, which one is wrong? Read. Yes, good. So what it says, macroscopic quantum tunneling was observed in superconducting circuits at ultra low temperature. Yes. Then a Josephson junction uses a thick metal layer between the two superconductors. No. First of all, it is not thick. Other, it is not a metal layer. Metals are usually conductors. You need insulator. So this is wrong. Then last is, tunneling means a non-zero probability of finding a particle beyond a classical barrier due to wave particle duality. This is right. So answer becomes 1 and 3. That's it for the class. Sometimes I think I should not pick all this. I should tell you that Nobel Prize में कितना पैसा मिलता है, $1.3 million, this, that. Okay, thank you.